I'll talk about two simple things, regular expressions and types. Both are simple, hopefully. So, and when you combine two simple things, you still have one simple thing. Okay, me, I'm Oleg. I'm known on internet as that nick. Don't try to pronounce it. It's cryptic on purpose. I work at Futurize, and I co-organize Helsinki Haskell user group meetup. So if you are around or from here, to come to our meetups. And just to mention one thing, I'm a release manager of Servant. It's a Haskell web framework, and it's known for good or bad for its use of types, and this talks about types as well, so it's just, I'm hopefully know something about types. Okay. So I'll start with an example to motivate the whole thing. Like I hope that you all are familiar with find utility, and if you look up its documentation on man pages, it says in synopsis shortly that this is how you use find. And because this talk is about types, you think, what is this? Is it like stringly types? But it's not kind of really stringly types, because there's those flags, and flags are kind of different than parameters. So if you write a spec for it, you will probably use keywords. I'm not sure if it's a real or valid spec, but hopefully it is, or right enough. So if you would use the find, in shell, we will just pass a list of string arguments. And some string arguments are a bit different than others. But in Clojure, we will, if we had like one-to-one API as close as possible, we will use keywords, but still it's list of arguments. But what if I tell that in Haskell we could write, do you see behind me, find as that, and it's valid Haskell. Like, it's a list of arguments with kind of special keywords and string in between. You won't believe it, but I'll explain how you can make it work. So first, about types. Type systems are introduced with rules that look like those. And this one is introducing a pair. It says that pair, we write pair as pair xy, and it has type 1 times b and blah, blah, blah. But I'll take it slow and explain it in a bit. So those rules, there's two parts. Below is the thing we are talking about. In this case, it was pair. And above the line is the premises, what we need to construct a pair. And if we look back, there was two parts we need. And when we do bigger programs, we stack those rules, and so the conclusion of previous one is a premise of next one, that way. And to walk through other bits, the gamma, I don't know why someone picked Greek letter, stands for context. It's like all the variables we have in scope. So instead of writing everything out, like x has type int and y has bool, we just use one letter. So when it's all over the place, then it's just one letter. So it's a small abstraction. The turnstile is simply a symbol. It doesn't have any special meaning. It's syntax. And we read it in the context gamma. And then there's a colon. It's is type of. So on the left of the colon, we have an expression, in this case, pair xy, and on the right, we have types. And I use different colors so you can follow which namespace kind of things are. And you kind of can read those rules out loud. So in any context gamma, pair xy has a type a times b, given that in the same context gamma, x has type a, and the same context y has type b. And that's it. So that's why people who do that like this notation and don't write it out because it's a mouthful. So hopefully you understand this. That's, if nothing else, then after this talk, with this knowledge, you can read type system papers and implement them and understand everything. And types will be at least a bit easier for you, like their relations. So, and there are more rules. Another thing in type systems is questions of decidability. We can ask some questions, and we want to know if there's an algorithm which says yes or no. So if something true or false. And one question is type checking. It's like the minimum you would expect. Like if given a program and I claim that it has a type, program X and type alpha, then is there an algorithm that says if this program is type correct? And you would like that, to get an answer either yes or no, and if it's no, to get an error message as well, like comprehensible one. And you might imagine this is a common thing. Actually, it's not, because I didn't try, but you can write Java program which compiler will just say that, sorry, I don't know what you mean, and will reject it, even it's a type correct program. So it's Java's type system is too complicated to computer to understand. The second property is typability or type inference, and like in an Elm talk, that's a cool thing to have. So you can write your program and then ask a computer what type is this. And if the type is what you expected, then you're like, yes, I probably wrote right program. And we can easily achieve this property if we require programmers to add type annotations everywhere, like in Java, for example. But it's tedious, so we want some level of type inference. I would say that I won't use any language without some rudimentary type inference, because why? Computers are smart enough to figure that out. But the third property is most like the holy grail. It's like I give a computer a type, and computer gives me back a program. So I write a type, and it gives me a program. So that's kind of where programmers could be put out of a job, because if business people could write a specification, then computer could generate that program. So done. In practice, it's, well, writing good types so that program does what you expect it to do is hard, but in easy or simple type system is possible, and it already helps a lot. So I'll walk through one example. Yeah. So the system I presented is that every property is decidable, so you can make computer do things for you. So, for example, this type, you who wrote some Haskell Elm pure script may recognize it. It's type of query. So given a function which takes a pair, give me a function of 2 arguments. It's like, well, simple thing, but you have to write it. Or do you? Because computer can figure that out. So because we need a function, it knows that we need to construct a function. So it uses lambda rule. And now from empty context, we have some function, function name I pick f, with a type a times b to c. And then we still need 2 parameters, so we use lambda rule 2 times more. And then we need to construct c. And I abbreviated the context with gamma, so I don't need to repeat all those three variables, and that's at the bottom. So how to construct C? Because C is like just C. Then we look what we have in context, and like we cannot use Y because it's wrong type. X is wrong type, but then f is a function which returns C. So let's try to call it. And we use var rule to use a name, and then we need a parameter for the function, and we need a pair. And pair is constructed with a pair constructor, and it takes 2 arguments. First need to be A, and second need to be B. We have A in the context, and we have B in the context. And that's what computer can do for us. Like for simple languages, it does for us. And if you don't know, the pure script calls it typed holes. So you can leave a hole in your program, and then computer or compiler will tell you, you need to fill this hole with this type. And then you can figure out, and then it also tells what is in the context, so what you can use. And so you can have dialogue with the compiler. Like, I don't know what goes here, I leave a placeholder, tell me what I need to do next. And it's very nice interactive development flow, but it's not REPL-like interactive, it's different kind of interactive. Okay, enough types. Next, regular expressions. Regular expressions, not as in Perl or POSIX regular expressions, so not the ones on the strings, but abstract concept like some of you may learned in computer science classes, like the stuff with automata and Turing machines and so on. So regular expressions could be empty. It could be just a character. Well, character is, I don't know what could be a better name, atom. And we can concatenate regular expressions or then form a union of them, either left or right. And one cool thing that regular expressions has is a clean closure, so it's 0 or many occurrences of this thing. So that's what makes them kind of interesting, like because concatenation and alternation is very simple, and closure makes stuff interesting and a bit difficult as well. So we all have some kind of intuition when we talk that these regular expressions should match this string. Like we kind of know, and then we have the similar intuition that this is kind of strings I want to match, and what kind of regular expression I have to write. And this is, we have intuition, and it's not precise. So like someone are better in that, and someone just cannot, and then there's problems with that, maybe. But we can formalize what means that this regular expression matches that string. So if example is, if I have a string or list of characters x, y, z, does it match regular expressions x or y star followed by z? So we can formalize matching in a funny looking way. So if I use that turnstile with 2 vertical bars to mean matches, and I have a regular expression on the right-hand side of R1 concatenated with R2, so what that would match? Well, we look what R1 matches. Let's say it matches some string delta 1. And I use Greek letters because there's more letters if you use Greek letters. And then there's R2, which let's say it matches string delta 2. So our concatenated regex matches concatenation of the strings, obviously. So, but obviously. And there's also more rules. So does this work? No, you cannot see it. Like the EPS rule match, if you have an empty regular expression, the only thing it matches is empty string. You might think it's not useful, but it's combined with a alternation, then we have an optional. So we can have empty or something. So it's maybe or optional. And then we have a clean star, which with rules I named nil and cons. You probably see where it's going. So a match will look like this. I really hope I had a pointer. It might look. So the outermost thing is a concatenation. So I use concatenation rule. And then on the left, there's just an atom, and then I have a clean star, and I use it once, I use it twice, and then there's nothing to use, and then left and right. So very simple, not complicated. But now I have a proof. I can say this is why this regular expression matches that string. It's not like computer says yes. It's like this is a proof. Okay, and that's what I almost said already, that those rules look very familiar or similar, like the pairing rule and the concatenation. So why we won't just throw away pairs and either and the ordinary list and just have superpowered regular expression list, R list, so which is indexed by regular expression of types. So we don't need pairs, sums, ordinary list. We only need super R list. But what's the point, you might ask? Why so? That if we still have pair left cons nil on the right, on the left, and it's bulky, but the same as we would write if we had pairs and lists and either. But on the right-hand side, we have a type which is like monstrous. What does it mean? It probably generates nice errors. Why we would do that? But the catch is that we can have nicer syntax. As our list is a list, we can use list syntax to write those. So we just write 1, A, B, and computer figures out how it matches to whatever pair list stuff there was underlying. And does it work? Well, does it work because I wouldn't give a talk here otherwise, and it works because the matches relation is decidable. There's a program which can say why it matches, and then we can translate it into a program which we don't see, but it's there. And I wrote a type checker plugin for GHC, the Glasgow Haskell compiler, so I can show you in a moment that it really works. But before that, if we come back to find example, if we rewrite clojure.spec or write a regular expression directly from the synopsis, it's in my notation would look like that. It's either flag H, flag L, or nothing, and then some string arguments, and then operand expression. So I like custom infix operators, by the way. And it translates almost one-to-one to Haskell. I swapped the order of empty. And then we can have a function find, which just takes a list with regex shape find and does something to your computer in I/O. So let's have a demo. Hopefully, no demo effects. OK. So, and as you see, I have to enable only 3 extensions. So it's not magic, just 3 small pieces of magic. Then I enable clean plugin. Clean is a person who did stuff relating to regular expressions. And then I enable dcorelin, because if my plugin is broken, then GHC will compile, bark at me and not just produce segfault. And for the demo, I don't have type signature, because even it's a good style to write them, but I wouldn't, because it looks like more dynamic. So the first thing is double square brackets. So if I look at its type, it's heterogeneous list of bool character and list of character, which is string. And if I print it out, then it expands the syntax. So it's there's triple colon heterogeneous cons. Next syntax part is a parents and square bracket. which creates relists. I have to give a type signature for it because otherwise my plugin won't know which regular expression I want to match it with. So if its type is a star of Boolean concatenated with a char, so alternating bool and char. So I have true, t, false, f. And I can print it out, and here you see the match expression. There's match C, which is cons, match V, which is var, and then there's match N, which is nil. It's like it is there, but if you, and it's tedious program which you wouldn't like to write, and what the compiler plugin does, it figures that out for you. And then double parentheses are call syntax. So the first argument is a function, and the rest is a R list. So it's intentional, so it looks like Lisp. And if I call this function, which is find underscore, and I want files, which I say by type F, and into directories. If I run it, if I run example call, then it outputs it in, then I have a bug. Well, that's what happens, because F is translated to D and D is translated to F. I fixed it this morning, and I fix it again. Okay, but it kind of works. And I said about error messages. If I use something else than D and F, then like those bottom errors are what GHC says to you, so it's like no idea. But then my error message, which is on top, just say, I'm expecting D or F. I didn't had time to narrow that red part to just the hash X, but it's possible. So it's just more engineering. But it could say that here's where you made a mistake. Okay, that was error. Let's fix it so I can run stuff. And for example, unions are nice because I can expect either char or bool, and then in my function, if it's char, I just print it, but if it's bool, I negate it and then print. So I can run, but the syntax is just either one. So I have to load. X1 prints character, X2 prints false. Okay, and then one thing which I made like 2 weeks ago is a T-type. It means it matches anything. And I think it's kind of nice and useful, because if I have just one bool somewhere in the list, it will find it for me. So there I have stuff, true, and more stuff. And it finds it true for me. But if I have two booleans, then it says I can match it in two ways. And it's like something top, and then times bool and top, or different times top. So then you can print explicit for alls. Then it will print more stuff for you, but here you see that first times matches char char bool bool char, but second one matches just char char. So it has two matches, and it doesn't. It wants unambiguous match. So it actually catches an error. If you pass 2 booleans, then it will say, I don't know what you want from me. Fix your program. Let's fix it. OK, how I'm on time? OK, then I have to conclude that hopefully you like that, but think it's cool. And what I would want it to do is use this syntax, but get those types, but cannot get everything in finite time. And thanks for listening.
Thanks, Oleg. We started a bit late, so maybe 1 or 2 questions, if they're short. I'm not surprised. Panu, this 6th question of yours.
I always seem to have something. Do you agree that this is especially suited for kind of list-oriented situations? Because I noticed that you started with defining the catenation as forming a pair, but pair forming is not associated, whereas catenation is. So kind of, is this why you are mainly working with lists? Because their catenation is associative.
Well, one thing is that it is meant to be fun, so don't use anything like that in production. And in abstract sense, if you have a pair of something in another pair or other way around, you can transform freely, so it doesn't really matter. So similarly, either you also can group them in different ways, but you can also translate. So there should be an alternative of either for many variants, as they call it.
Yeah, 1 more.
So do you think it would be possible to go beyond regular expressions to context-free grammars?
Yes, it will be possible, because you could decide on context-free grammars, but we don't have a concise syntax for them to write in inline. So that's the problem. We need it wouldn't be useful, because if we need to write blob, then it won't work.
All right, thanks, Oleg.